Hey, welcome to yet another graduate seminar. We have Phil talking about the search for decision reduction for code equivalence. Enjoy and good luck.
Thanks. So I think this is the last talk, right, for this semester for the grad seminar, right? So we saved the best for last. Today I'm going to provide a counterexample to that statement. So, all right. So just some motivation for why this talk is important. Just from a mathematical perspective, I think this is a pretty cool method. So normally when you were trying to, if you're trying to construct something and you want to say if a construction exists, you would try and get that construction, and then you could, if you could find it, you would say, yes, this construction exists, or no, this construction doesn't. But this is actually going to go the opposite direction, so it's going to ask yes or no questions to actually construct something from it. So instead of constructing and then concluding, it will sort of say yes or no about something and then get the construction. And then if you don't care about the math part, there's also like a cybersecurity or cryptography scheme that uses and it relies on the hardness of trying to solve code equivalence to what was it? Yeah, it relies on the hardness of solving code equivalence to be safe. So if you were trying to break this cryptographic scheme, it'd be the same as trying to solve code equivalence. And if that's a hard problem to solve, then we say that this crypto system is safe. But the thing is, at the moment, we don't know if code equivalence can be efficiently solved or not. So
You're trying to, this is a complexity reduction. You're saying if this thing is this complex, I can reduce it to another problem, so it must be the same complexity, that kind of stuff?
Similar. So what this is actually going to do is it's going to give another avenue that you could try and solve code equivalence with. Because what this will do is if there's a way to say yes or no, a code equivalence exists, this will actually give you the construction of it. So now that I've attempted to motivate some of the talk, we can now informally and then formally define some of the things in coding theory. So informally, so suppose you are you're talking on the phone, and there's a lot of static on the phone because you're getting bad reception or something, and you want to spell something, right? So say you want to spell, so you're talking over a noisy channel, and you want to spell the word Ben, right? So, for example, if you're at Starbucks and you want a simpler name, and you want to, and you're ordering over the phone for some reason. So say that you just spell it normally, so like BEN, but you're in this noisy channel, and so someone just for the B part, say they only hear the E sound at the end, right? So on their end, they don't know if you said B, they don't know if you said D, or any other letter. And so the question becomes, when there's all this static, how can you send these letters over, still be able to recover them on the receiving end. So if they received like EE, somehow they'd be able to recover what the original letter was. And the solution would be to use code words for a specific letter. So like instead of saying B, maybe you say like Bravo instead. So like the NATO phonetic alphabet, I think, is what they use, right? So you say like Bravo, whatever. I don't know the NATO word for E. Yeah. But the thing is, now, because the words in the NATO alphabet, they differ by so many sounds. If you only heard vo at the end, that was received, then there's only one code word that ends with vo. And so, because that's the case, you could recover and say, hey, this person actually said B. So let's see what else. Yeah, imagine ordering as Paneth. Paneth? So just as a note, we want our code words that we encode our letters as, we want them to sound as different as possible, because if instead we encoded B with Bravo and C with like convo, right? If you received vo, then you have the same issue as before, where you can't uniquely say which code word had that vo sound at the end. There we go. N is November. So now we can sort of formally define elements, what it means to be a code. So this is sort of like a sound version of coding theory, where it's like we want to use code words and we want them to differ by as many sounds as possible, so that when the noise erases something, we can uniquely determine what code word was sent. So now we could formally define stuff. And this, I think I can write more for. And so now instead of word like sounds, we're just going to use numbers. So definition, let fq to n be n vector space over and then fq, if you're not familiar, just think of it as the set, or it's isomorphic to the set 0, 1, q minus 1, where q is some prime. And then let C just be a subset of this vector space. So in this vector space, just what elements look like is just an element A1, A2, dot, 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 AN, where AN lives in that, or AI lives in that set.
So you use subspace or just subset?
So it's literally just a subset.
Okay.
So We'll care later if it is a subspace, but just in general, if C is a subset, then we call C a code. Oh, sorry. Then C is called a code, and the elements C in C are called code words. So I take a subset of FQ to the n, and any element in the subset is going to be called a code word. So, and then we say the length of C is n. And the length just means how many coordinates are in each code word. So there's n coordinates. So we say the length of C is n. So now something that's important to coding theory, there's something called the Hamming distance. So let C and C prime be in the code so that these two are different. Then the Hamming distance, we'll just denote it by D. So the Hamming distance, this right here just means the set 1 to n. And the Hamming distance between two code words is going to be the number of coordinates where these two code words differ.
Hey, Phillip, so we have a question. So they're asking, what if we have an infinite dimensional vector space? Could this instruction still work?
I'm not sure if it would still work. Well, because like something like distance, when you have infinitely many like coordinates, you could say like that coordinates differ by infinitely many places. Ideally, we want this to be in a finite sense, so that you have like finitely many code words to deal with, and like finitely many things to represent, I guess, to encode. I think you could still make a metric, yeah. So, but like,
it's compatible with this. It's like of the form dc/ci divided by 1 plus c/ci, and with 2 to be ij plus c. And if you sum all those, it's always going to be less than 2.
yeah.
Always be less than 2. Distance will always be less than 2.
So, I'm not sure if it works still for infinite dimensional spaces, or like, I don't think you would get the same applications as a thing.
For practical purposes, you can't send an infinite dimensional code words.
That as well as you couldn't send it. So now the another definition. So the minimum distance of a code, we're going to denote it by D. It's going to be equal to the minimum Hamming distance between any two code words in the code. So we say that the distance of a code is just the minimum of any distance between any two code words. So just as an example, can I go here or is it too far over?
Not yet. No, you keep going.
Okay, so if you had your C being 1, 1, 1 and 0, 0, 1, say these were your two code words, then the minimum distance between these two, or actually, sorry, let me throw in a third. The minimum distance of this code would be 1 because this code word and this code word, they only differ by 1 coordinate. And yeah, that's the, I guess, minimum across all those pairs. Okay.
Why do they insist on calling it? Why don't they call it random names used more in quality?
Yeah, I don't know. I think that's just what they call it. And so a useful observation, it won't show up for the rest of the talk, but it's something important to note. Is that for a code C with minimum distance D, then we can recover up to D minus 1 erasures. And so just a notation thing, if you have a code word C equal C1, C2, dot, 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 Cn, like this, and there's an erasure, let's say at the second coordinate, then how we denote that is by a star. And so if this is what you receive on the receiving end, then this means there was an erasure at the second coordinate. And so what I'll just briefly show is that you can recover if there's D minus 1 erasures in this code word, then we can still recover it. And if there's D, then we can't. So suppose that there were D erasures, then because the minimum distance of a code is D, there exist two code words that have distance D from each other. And so if all the errors occurred on the D places where these two code words differ, then these two code words are exactly the same on the other coordinates. And so what that means is we're in the case where you have vo and two words that end with vo. And so we can't recover it. However, on the other hand, if there are only D minus 1 code words, there are no two code words that differ from each other at D minus 1 places. And so that means there has to be a unique code word that corresponded to like what's left over, because otherwise, if you had D minus 1 erasures and two code words that matched everywhere else, then the minimum distance would have to be at least D minus 1.
So wait, so useful observation is saying that if I take this code up here, delete one of the entries, I can uniquely find back my code word, right?
So in this one, D is 1. So this says this can't recover anything because.
But if I take the code word 0, 1 star, right? I can just
doesn't always work. If you delete that
It has to work all the time, yeah. So it has to be an erasure for any code
Is
word.
there an algorithm for actually recovering code word after d minus 1 erasures? Or is it just a heuristic? You just know you can do it, but you don't know an actual way of recovering the code word.
I think there is a way to actually
It depends on the code.
recover
If
it,
you have
but yeah.
permutation codes, then they all live in the permutation. If you have linear codes, then you just have to generate the matrices. You just do linear algebra. In this case, if it's just a random set of code words, then you just have to, it's an algorithm that just goes through each code.
You would just have to check every code word and check that it's distant. Yeah, but brute force.
Most codes are linear. You use like more complexity.
Yeah.
So there's additional later on.
There's more structure that would allow you to decode it easier. Yeah. So, all right. So we have that. So now, go back here. How am I doing on time?
You have, so it's 23, so we have another.
Okay, so I think I'm okay.
30 seconds.
So now, so we know the length of a code, we know the minimum distance of a code. Now there's one final property we'll consider. So another definition, linear codes. And so let C be a subset of FQCN. Then C is a linear code if C is a subspace of FQCN. So now is what you were saying is it a subspace? It is a subspace if it's a linear code, but in general, it's a subset. So we say the dimension K of C So because this is a vector space, right, it has a basis. So dimension is just the number of basis vectors. So this K is just the dimension of C as a vector space over FQTN. Okay. So now, in general, how we denote linear codes is we denote so a linear code with distance d, length n, and dimension k as so this is how we'll denote our linear codes. So if I just say let this be an NKD linear code, that just means that here. Okay. So now one final thing to note is the concept of a generator matrix. So hopefully this is the last thing or close to the last thing I'll need to define. So let B equal B1, B2, BK, B code C. shoot. So then the generator matrix for C is just B1, B2. And so essentially what this is a matrix whose rows are the basis vectors for C. So if you can come up with a basis for our code, then the rows of this matrix are then the rows of this matrix are actually the code itself is generated by the span of these basis vectors, right? So one observation you can make is that if you take any, so if x is in fq to the k, then x, so I'll call this matrix G. So x times G lives in the code. So the reason being, when you multiply something on the right, that will be a linear combination of rows. And any linear combination of these rows, because they're a basis, will be some code word. Okay, so one other thing is the generator matrix for a given code depends on our choice of basis. And so you can get the exact same code if you used a different basis. So what that means as well is for any generator matrix and any change of basis matrix, if you multiply them together, you will generate the exact same code.
So you say, I think when I asked earlier, you can use generator matrices to reconstruct any deleted code word?
Yeah, because you'd get a system of,
Just by linear,
yeah, you get a system of equations there. So now, okay. Now we can get, so this is most of the background for code equivalence. Now we can finally get to the core of the talk. Was everything clear so far? Okay. So I guess I'll erase this. All right, so I guess a final bit of definitions. We say that two linear codes are permutation code equivalent. So two linear codes, C and C prime, if there exists permutation So we say two linear codes are permutation code equivalent if there's a permutation such that the permutation of one code is equal to the other. And how we represent a permutation, or like how this permutation acts, is it will permute the the coordinates of your code words. And so if every code word in C prime is just some code word in C with its coordinates flipped around. So for example, this one, if I swap to the second and third code word, then this would stay the same. When I flip the two, this would be 0, 1, 0, and this would still be 0, 1, 1. But those two would be permutation code equivalent to each other. So an equivalent definition. So you could also just say let G and G prime be the generator matrices. For C and C prime. So an alternate definition is C and C prime are, I'm just going to denote it by permutation code equivalent. If there exists an S that's invertible and a permutation matrix so n by n, sorry, that's a bit small, P, such that you can write G prime equal to S times G times Phi. And so this S here, just think of it as a change of basis matrix, because because again, the choice of basis will change your generator matrix. And then this permutation will just permute columns of the generator matrix. So now that we have that, we need 3 key observations. We can finally say, okay, what was it? We can finally come up with our algorithm that will say yes or no questions to find a code equivalence between 2 codes. So the 3 key observations. And that's, so if G prime is equal to SGP, then 1, the number of times so if you have a code equivalence, the number of times a column is repeated. Sorry, is there a question? Okay. So if you have 2 codes that are code equivalent, then the number of times that a column gets repeated is preserved, right? Because essentially all we're doing is permuting columns. If you have 2 identical twins, right, and you tell them to stand over there, they're still 2 identical twins. You're not suddenly going to create one out of nowhere, and one's not suddenly going to disappear. So the next observation is 2. If there exists a column G and G such that Um, is sorry. Okay, so sorry. The second one it will say, if there is a column of G that is repeated exactly m times, and it's the only column in G that is mapped exactly m times, then what we can say is there exists a unique set in G prime of m repeated columns that these repeated G's have to get mapped to. And the reason being is, again, because of the first thing. It says that the number of times a column is repeated, it has to be preserved. So if there's only one set of columns that's repeated m times, it has to get mapped uniquely to another set of columns that are repeated m times. And so and G, or and, yeah, G is the only column. I feel like I'm just, I don't know if is it worth it to write? I don't know. So, okay, it's repeated. Sorry, I'm writing way down here. I hope you can see it. Okay, so that's the second observation. And then the final observation, and then we're almost there. Sorry, there was a lot of background to this. Is, where is it? So let P prime
When we say image, number two, the image under SP.
yeah, under SP.
Okay.
So when I apply S and then I apply P, then that sort of is the image. So number three is let P be a permutation of sorry, this should say of so this final thing to note is if you take some other permutation, and all it does is map repeated columns in G to themselves, then this right here will also be a coequivalent, or also a permutation coequivalence. And the reason being is, say you have like the word Mississippi, right? And I have a permutation that only changes S's with other S's, right? If I apply that permutation, then you're just going to get the same word back, because if I flip two S's around, right, it's not going to change the word at all. And so similarly here, if I take repeated columns that are just identical copies of each other, flip them around, then it's going to leave it completely unchanged. So now we can finally get to the algorithm itself. So the algorithm, how am I doing on time again?
You have 17 minutes.
17 minutes? Okay, I should be able to finish then.
Yeah, we don't have analysis, so you can keep going.
Go a little over? Okay. I think we should be able to finish in time. Is everything clear so far, for the most part? Okay. So what we're going to do is, here's why we can, so.
Sorry, P prime is a permutation of some repeated columns.
Yes, sorry. So now what we're going to be able to do is we're going to have an oracle, which we assume it exists, that can instantaneously tell us if a permutation equivalence exists between two matrices. And if such an oracle exists, then we can ask it yes or no questions. Are these matrices permutation coequivalent or not? And using this oracle and this algorithm, we'll be able to construct a permutation between two generated matrices. So let O be an oracle that can So step one of the algorithm. So we are given two codes, and we want to know if they are code equivalent or not. It turns out this will fail on the first step if they're not code equivalent, and if they are code equivalent, it will find it. So the first step is, or sorry, let me define everything. So let C and C prime be two codes, two linear codes with generated matrices G and G prime. Okay, so now step one, let M be the number, or the maximum number of repeated columns in G. So however many times a column repeats, this is the maximum number. And then the second step we do is we're going to create a permutation, and we're going to see how it acts on every single coordinate. So the permutation I'm going to be talking about is like this. So we want to know what index gets mapped where, but obviously we can convert that into a permutation matrix pretty easily. And so what we're going to do is we're going to ask how the permutation behaves on every single coordinate. So let's start with pi of 1. So we want to know what pi of 1 is. And we want to see if pi of 1 is equal to j for some j between 1 and n. So how are we going to do this? What we're going to do is we're going to let g1 be the first column in G, and we're going to let Gj or G prime j be the jth column of G prime. And then what we're going to do is we're going to create two new matrices. And what we're going to do is we're going to take G and we'll append m copies of G1 to the end. So we're adding m extra columns. And then similarly, we're going to take G prime and add m extra columns of or m extra copies of G prime j. So then we're going to ask the oracle, okay, are these two new codes that we generated, are they permutation equivalent or not? If they are permutation equivalent, then we can start applying key observations. If not, then we pick a different j. So for some j, the oracle is going to say yes. So if the oracle says yes, so let's say what we do next. So I'll call it G1 by appending and we'll create G prime 1 by adding Gj or m copies of G prime j to G prime. Right, so I add these, I ask the oracle, so I ask if these two are, so now say that it says yes at some point. So what this means, okay, is let's ask.
Where exactly are you adding the columns?
Oh, sorry, we're appending them at the very end. So the matrix becomes longer, or the length of this becomes longer. And now the question becomes, okay, how many, we want to know what the G1s are going to get mapped to, right? So G1 shows up at least once, right? And I added M copies, right? So the number of repeats is at least M plus 1, right? And then similarly for GJ prime shows up at least once. I added M copies. So the question is, where are these being mapped to, right? So these G1s, because there's at least M plus 1 of them, and in the original, the max was M, it means that the G1s are repeated at most M plus 1 times, or sorry, at least M plus 1 times, and that by fact 2, because no one else, or none of the other columns can be repeated that many times, it has to be the case that the repeated copies of G1 get mapped to the repeated copies of G prime J. So that's by key observation 2. And now what I can do is if I consider so I know my steps, I'm not writing all of them, but if you consider the permutation, let's call it P prime, that maps, it's going to map the repeated G1s to the repeated GJ primes. They both have the same size, so there is a bijection between them, which means there's a permutation between them. And so this permutation, I'm going to select it such that P of 1 from the original code equivalence gets mapped to J. And so what this means, if I apply the permutation found in the code equivalence, and then I apply P prime to it, then what this says is there exists, by fact 3, or observation 3, if I compose the two, it's also a permutation code equivalence. So there exists a permutation code equivalence such that I'll call it pi of 1 is equal to J.
So I'm a little lost. So what does this algorithm do?
So what it's going to do is we're going to create this permutation, but we're going to create it by how it acts element by element.
So the oracle tells you that if two codes are PCE, this algorithm is constructing for us the actual
permutation between them. So this says that pi 1 gets mapped to J. So we've only said how this permutation behaves on the first coordinate. That's all we've said so far. And so now the question becomes, okay, I've found a way, if you believe me, to say how this permutation, just by asking a yes or no question, how this permutation acts on the first coordinate. Now the question is, okay, how do I find it for the second coordinate, the third coordinate, and so on and so forth, right? So you would think that what you could do is you could just repeat the process again for 2, and then repeat it again for 3 on the original generator matrices G and G prime. Now the issue is that permutation equivalences, they're not unique. So the thing is, if you find a permutation equivalence that sends 2 to some other value, it might not be the case that that permutation agrees with this one here. And so it's very close to just repeating the process. But what you have to do is, instead of repeating the process on G and G prime, you have to repeat this process on G1 and G1 prime. And then we append a different number. So let me sort of explain. So repeat on G1 prime and G1. So the only difference now is when we repeat on these two matrices, instead of appending m copies of our two candidates, what we're going to do instead is we'll append 2m copies. Because what will end up happening is, so for G1 and GJ prime, the number of repeats here is at least m plus 1, right? But it's smaller than 2m. Or it's less than or equal to 2m, right? In G1 prime and G1. So the number of times it repeats lives between these two values. So if I take G1 and G1 prime and I append 2m copies, then G2, and let's say I don't know, J prime is probably a bad, it's okay. So the number of repeats of this column is going to be between 2m plus 1 and, so let's say this is like the number of repeats. So the number of times G2 is repeated in this new big matrix is between here and here. And so what ends up happening for these values is I'm going to find, if I extend this to the end and I say at the very end that you've found a permutation equivalence on all of these after repeating the steps, right? Then G1 and GJ have to be images of each other because they're the only ones that can have that size. And then I apply step 3 to get a permutation that sends 1 to J. And for G2, it's the only one that's repeated this number of times. No one else by construction can be in this interval as well. So the G2s have to be mapped to these uniquely. I apply step 3 again to say that there's a permutation equivalence between sigma 2 and J prime. Or sorry, 2 and J prime. And then finally, what we'll get at the very end is we'll get that there exists a permutation equivalence such that pi of 1 equals J, pi of 2 equals J prime, and then dot, 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 pi of n equals, I don't know, J double prime, something like that, right? So we'll know where all of these get mapped to. But then you'll also have other stuff because I appended columns, the permutation equivalence will go farther and farther and farther. But the thing is, on these n plus 1s, these are all going to get mapped to columns that we added. So these n plus 1s, they're going to get mapped outside of columns that were originally in G. They're going to get mapped to ones that we added. And so what we can do is if we just ignore the permutation at n plus 1, then you get a permutation. We know how it acts on the first, the second, all the way to n, and that will be the permutation equivalence between these two matrices when we convert it to a permutation matrix. And so this is the part I was really worried I would lose a lot of people. But yeah.
The pi, right? How do you pick the pi again?
So we ask, like, is column 1 going to get mapped to column J? And so we ask we want to figure this out.
Okay, so that's part
Because, so if at some point the oracle says yes, then it exists.
Right.
So if it says no, then there does not exist a permutation that maps that to that.
You go back and you select a different one?
Yeah, and you go back and you select a different one. And so you keep repeating until you get, so a yes at the first step, a yes at the second step, a yes all the way to n. And then finally, that will tell you.
And you're saying that along this process, as long as you pick from 1 through n, those get mapped to the original columns?
Yeah, so how I'm picking my j's, I'm picking my j's between 1 and n. So on the first n steps, the j primes will live between 1 and n. Yeah. So, yeah, I think that's everything I have to say. I know I'm running a little over time.
Any questions?
Um,
I have some. So first thing is, this looks like it's the complexity of this is around like what, big O of n squared?
yeah, I think it runs in like n squared time as long as the length of the code is like small enough, I think. So in the code, in the paper that this is based on, it actually gives the exact like complexity, like in the restriction. So it's like as long as the length is like this short, then it runs in like n squared time or something like that.
So so in that case, this is essentially a complexity reduction.
Yeah.
So if this oracle can be expressed in polynomial time,
Then the entire thing, yeah, can be done in So, but what that means is this oracle just is literally, it's not even constructing an equivalence between them. It just says yes or no. Are they equivalent? Are they not? So as long as you can say, as long as you can say, even without construction, whether two codes are equivalent or not, then you can construct the equivalence.
Right. So,
yeah.
And this oracle, there's got to be, since we're working with finite fields, there is an algorithm that just isn't in polynomial time. Right?
Yeah, that's what we don't know. So.
But isn't there an exhaustive? It seems like since we're working with finite fields, isn't there an exhaustive algorithm?
Or sorry, but we don't know the time complexity of that algorithm, whether it's polynomial or exponential.
Oh, I
think, yeah.
It does exist. There is
it exists, yeah.
What's the complexity of this algorithm?
So this one is like x squared, I think, is what it says. So like it doesn't give any explanation in the paper, unfortunately, so I couldn't really tell you like why, but it says as long as the length